Welcome back. This lecture is about how I can use Floquet theory in data-driven fluid simulation. I have listed here two papers, very interesting paper. Well, the first one is in French, so perhaps many of us cannot read it. I have listed it here to indicate that this idea was known since 1883. The paper was published since 1883, and after that much work has been done about Floquet theory. And also, I don't want to illustrate Floquet theory today. Rather than I just want to give you some idea that Floquet theory is something exists, and it is something very useful. uh, if you already know Floquet theory, then you might go back and then take a look at it, what I'm talking about. And if you don't know Floquet theory, maybe it will be a good idea to find some reference paper and try to understand Floquet theory. The second paper is about application of Floquet theory in fluid simulation, and obviously this is written in English. You can download it. If you Google with the title, you will get a free copy from either author's website or ResearchGate, or you can get it from Journal of Fluid Mechanics. So this paper it was written in 2007, so quite some time ago. So that means the Floquet theory is not something new. It was there, so you can have some brief idea about how Floquet theory can be used fluid flow analysis. What I'm going to show you here, there are something else can be done in Floquet theory. Let's look at this Navier-Stokes equation. You look at the left hand side and the right hand side. Forget the middle term. So the left hand side is time derivative of u, and right hand side is all terms for incompressible Navier-Stokes equation. What Floquet theory states is that you can perhaps write this nonlinear partial differential equation in terms of a matrix A, which depends on time, and then multiply with the solution vector u. It's kind of a linearization or linear representation of the partial differential equation, and that is all about Floquet theory. Is that now you can look at the eigenvalues of the matrix A. Well, obviously you have to determine the matrix A, and then you can analyze the stability of a fluid system or a dynamical system, and that's very interesting idea. So what I'm going to do is that instead of doing the stability analysis, I'm going to take some fluid flow data as a time snapshot. So I'll consider this u vector written here is a fluid velocity. So in some domain I have some grid points. So all grid points I have a fluid velocity at time t1, and then I go to the next time step, time t2, and so on. So every time step I have a fluid velocity. I collect all the fluid velocity and try to see that if I have the time derivative of the fluid velocity, how does this time derivative correlate with the fluid velocity itself. So du dt equals a matrix A times u, and try to find this matrix A. And I am saying here is that, well, the Floquet theory is saying that the matrix may be dependent on time. So what I'm going to do is trying to find the best possibility or the best matrix A using any of the optimization technique, and then run this dynamical system again. So du dt equals now A times u. So let's make it clear. let's see if I have a mouse. Yeah, I have a mouse here. So first I take the Navier-Stokes equation. Du dt equals Navier-Stokes equation. Solve Navier-Stokes equation, get some data. Okay, and then I take the data, find this matrix A. Once I have found this matrix A, then I solve this linear system, and then I want to compare the solution with what I had the original solution. So it looks like that if I have some data, using the data I can construct this dynamical system, finite dimensional dynamical system, and that is why it is called data driven fluid simulation. So now you can run this finite dimensional dynamical system, and then you can simulate. Maybe originally you have some time snapshot. Perhaps if you know A, you can go further. So in other way, that fluid simulations, we know that they're very costly. So you do some costly simulation, and then use that. Maybe you generate a reduced dimensional somehow. You find a matrix using Floquet theory, and then you can perhaps do some simulation. So let me see if I can find an animation to show you. Okay, so in this simulation, the top one I labeled as CFD simulation. So this is done by solving Navier-Stokes equation in velocity form. Okay, and then I collected the vorticity. Okay, and then I used the vorticity to simulate the vorticity equation in terms of that matrix A. And then the bottom part, which I labeled here as data driven simulation. So this is done with the Floquet theory, and then I want to compare, see how do they look like. So if I animate that, I can see that they're fairly similar. Of course, there are some noise we can see in the data driven case or Floquet theory prediction. But if we carefully look at, we can see that the dominant pattern of the flow is adequately captured. We can see that from the vortices are shed from that airfoil. So I should have mentioned that this is an airfoil simulation, but this is perhaps not needed, because this is something I just want to give you an idea that how it works. And this is something interesting that I will perhaps continue discussing. So hopefully you enjoyed this brief presentation, and if you have any question, please feel free to contact me. Thank you very much.